Welcome to homework.
This problem tells us that we have a lead sphere and an aluminum sphere of the same mass, and our job is to find the ratio of the radius of the aluminum sphere to the lead sphere. Now throughout, I'm going to use Al, the atomic symbol for aluminum, to represent aluminum, and Pb, the atomic symbol for lead, to represent lead. Now our general game plan here is first I'm going to use a mass of 1 kilogram for both of these spheres, just to make the calculations a little bit easy and also to avoid having too much of a symbolic mess. So I'm choosing this arbitrary mass of 1 kilogram. Our general game plan is going to be to take the mass of each of these spheres, use the densities of both of these materials, which we can look up, use that to turn it into the volume of those spheres. And then we're going to use the volume to find the radius of those spheres. In order to do that, we need to know that density is equal to mass over volume. We need to know that the volume of a sphere is equal to 4/3 pi radius cubed. And we also need to know the densities of these two materials. The density of lead is equal to 1.13 times 10 to the 3 kilograms per cubic meter. And the density of aluminum is equal to 2.7 times 10 to the 3 kilograms per cubic meter. So let's get started. First, we'll deal with finding the radius of this lead sphere. So we will start there. So, to find the radius of our lead sphere, again, we know that our density is equal to 11.3 times 10 to the 3 kilograms per cubic meter. We know that because density is equal to mass over volume, we can rearrange that, say volume is equal to mass over density, which means that our volume is equal to 1. We chose that arbitrary mass 1 over 11,300. I just moved it from scientific notation to standard notation, and that would be in meters cubed. And what we can do once we know that volume, I'm not going to put that into a decimal form for now. I know that that volume is equal to 4/3 pi r cubed. I got that from knowing that the volume of a sphere is equal to 4/3 pi r cubed. What I'm going to do now is I'm going to rearrange that equation to solve for r, and that's going to be the first thing we are looking for. If we rearrange that, we know that r is equal to the cube root of 1 over 11,300 times 3/4 times 1 over pi. We do that calculation, and we find that the radius of our lead sphere is equal to 0.02765 meters. I'm not going to do any rounding quite yet. Let's now find the radius of our aluminum sphere. The density of aluminum is equal to 2.7 times 10 to the 3 kilograms per cubic meter. Again, from before, I know that volume is equal to mass over density. So what I can do is I can use my arbitrary mass of 1 over our density of 2,700, again, moving from scientific notation into standard notation. What I can do then is I can say that that volume is equal to 4/3 pi r cubed, our volume for a sphere. I will rearrange, and I will end up with the cube root of our volume times 3/4 times 1 over pi. The way I get from our original volume expression to this new radius-centric expression is I multiply by the reciprocal of 4/3, which is 3/4, multiply by the reciprocal of pi, which is 1 over pi, and then to isolate that r, the r is being cubed, so I will cube root the entire expression. When I calculate that, I find that the radius of our aluminum sphere is equal to 0.04455 meters. This is the second piece of information that we need. And now we're going to solve for our final answer. Remember, we're looking for the radius of the aluminum sphere to the radius of the lead sphere. Now, because we chose an arbitrary mass, we don't know what these radii actually are, but we know that we use the same mass in both, so we can still set this up as a proportion. So using our arbitrary mass, we found that the radius of our lead sphere was equal to 0.027645 meters. We found that the radius of our aluminum sphere was equal to 0.04455 meters. Just a quick check. It would make sense that the aluminum sphere is larger than the lead sphere because aluminum has a lower density, so it's going to need to be bigger to have the same mass. We are looking for the ratio of the radius of the aluminum sphere to the radius of the lead sphere. So I can set that up. So it's our radius for the aluminum on the left, radius for the lead on the right. That is our ratio. We can compute that down to a final number by dividing the radius of our aluminum sphere by the radius of our lead sphere, and we will end up with a final answer of 1.6115. That is the ratio of aluminum to our lead radius.